Before the next speaker, I want to add one thing, in that many of the projects that you've seen this year involve hardware. And I'll have you know, as a testament to the hard work of each student, we don't teach anything about hardware yet. We will next year, but everybody had to learn all of this on their own, so I'm very proud of that. Ladies and gentlemen, let me introduce to you our final presenter, James Ratini.
Hi everybody, as Perry said, I am James, and I'm going to be talking you through growing Dungeons & Dragons maps. So, my capstone project is using a genetic algorithm to grow maps for a specific game, which is Dungeons & Dragons. Before we get into the technical side of what a genetic algorithm is, I want to talk about it conceptually. It is an artificial intelligence algorithm used in software to evolve solutions. It's best used when there is no single optimal solution to any given problem. So if you think like a broad spectrum of possible solutions to any problem. So what problem am I trying to solve myself then? In short, fun. Fun is a very subjective thing. What I find fun and what you find fun are often going to be very different. Unfortunately, trying to create something that's fun from scratch with no framework would be incredibly difficult, so I narrowed it down to Dungeons & Dragons because that is a game that I enjoy, and I have a lot of friends who play, so I was able to get feedback from them. So what is a genetic algorithm technically then? There are four primary parts to this. There is a selection phase, which is when we figure out which parents will be used in the crossover process, and crossover is when parents share their genes with their child. Mutation is the process of randomly selecting those genes to alter them in some smaller, sometimes larger way. And then fitness, which is easily the most important aspect of this entire process, is a mathematical representation of what I have defined to be a fun map. Genetic algorithm and map design. So the selection process that I used is referred to as fitness proportionate selection, which is mostly what it sounds like. Each map, if you look at the pie chart up top, each map is given a fitness score. Map 2, which is red, has the highest one. So if you were to close your eyes and throw a dart, the highest fitness score is most likely to be hit with that dart. Crossover, pretty simple method I use. For each gene, there's a 50% chance that you will take from parent A and a 50% chance that you will take from parent B. Mutation, there's a small percentage chance, in my case it's 0.5% chance, and that any of these genes will mutate. On the right again, you can see a list of some of the mutations that I use. So if we look at monster, because we're playing fantasy, we have shift position, which just moves the cell in any random direction, some odd number of tiles. Change, which if it starts as a monster, we might change it to a wall or a room or a hallway. And then the mutations that have a red border I refer to as context-aware mutations. In order for a cell to undergo a context-aware mutation, it must meet a certain prerequisite. In order for a monster to undergo a hide around corner, we evaluate the surrounding area and deduct if there even is a corner for it to hide around. This offers a bit of surprise to the players who might be playing this game. If they enter a room, they see nothing there, and all of a sudden, out from around a corner pops the boss. Another good example of context-aware would be the room mutations contract and expand. If you expand a room from the center of it, you don't really go anywhere. However, if the cell we are looking at is on the wall of the room, expanding can allow us to make the room grow in a random way, as well as shrink in a random way. Genetic algorithm map design. So fitness, again, the most important feature. Some of the aspects I looked for in any of the genes. Always I expected to be long and narrow. Sometimes they were kind of windy. I wanted them to contain branches that would occasionally end in dead ends, as exploration is often a very fun aspect for players. If you look on the far right, you can see one of these example maps. So the usually one wide or one tall or one wide sections are going to be hallways. You can see sometimes they end in dead ends. Sometimes they lead straight into rooms. So rooms are, I wanted to be decently spread apart. This in some cases is, but if they weren't decent, if we didn't try to make them decently spread apart, they would often just clump together and form this huge blob effectively. We usually want them to connect to at least one hallway so they're actually a part of the players are able to reach at any point. Monsters in large groups of 3 or more, usually we would consider harder encounters, I suppose. So we want them to be in rooms, so players have room to move around and to do whatever they want to do. Smaller ones can be farther away from each other inside of hallways, so they can sort of be patrolling the area and such. There are other things going into this other than just these genes. Like if no monsters exist on the map, we really see no reason for this. So this is some process pictures. This is a map at generations 250 and 750. You can see it's 700. This is an incomplete map at this point. You can see at 750, we've added this room. We've changed this large thing. Down here, so in 250, there's just this kind of ugly branch of a hallway that leads to nothing and has nothing down here that's worth going to. In 750, we've turned it into a room, effectively. In 250, there's just some things scattered throughout. If we go on to the next, we can see on the left 750, which we just saw, and then generation 1000, which is the completed map. We've gotten rid of some of these spare things that are just sitting around. Sorry, the green squares are monsters, the purple are treasures, and the yellow are traps. We've made this hallway. It's a bit less straight, so it has more of a windy curve to it. We've added some dead ends, it looks like. Everything is connected now, so we can actually get to these things that are just floating around. So some of the technology I used, I solely wrote this in Java for a few reasons. Some of the pros are that it's object-oriented, which is conducive for reusable code, as well as it's easy for me to visualize the different interactions going on between all of my objects. It also offers a large number of libraries, so it has most of what I could possibly want to do. And I have familiarity with the debugger, which came in a lot of use when things got sticky. Also bonus, Java is in demand in the job market, so being able to say that I did a project this large with it is worthwhile in the future. So it does have some cons though. Everything in Java is effectively passed by value, which make recursion a little tricky sometimes, so trying to navigate through the maps recursively. I have no control over memory deallocation, which was a huge pain occasionally, as the process would lag as garbage collection would come through and pick up everything I left behind. No multiple inheritance. Java does have features to get around this. However, there were some specific instances where I would have liked multiple inheritance. So this is the process of the application. We start at generation 0, and instead of wanting to start with something totally random, I gave it a bit of a framework. So I scatter some mostly square-like rooms throughout the map, then generate a perfect maze around those rooms, and then scatter the map with treasures and traps and monsters and whatnot. Then we enter the selection process where we order the maps by fitness and then do that fitness proportionate selection that I was referring to before. Entering crossover, same thing for each of the types of genes, hallways, rooms, traps, treasures, monsters. 50% chance that we take a gene from parent A, 50% chance that we take from parent B. Entering a mutation, we iterate through each of the genes and select some of them for mutation. If they're selected, they mutate. And then the fitness function where we evaluate all these things that are now in the child. We repeat this X amount of times, X being the number of generations that you would hope to achieve. Some of the biggest setbacks. My original design used each individual cell within the map as its own gene. This resulted in something totally random at every step of the way. Because you would take, at cell 3232, you would either choose parent A or parent B, and it was almost impossible to get anything that even looked remotely like a map. So during the redesign, I decided to treat connected blocks of room cells or hallway cells or whatever as specific genes and pass those on as groups. The issue with that is during mutation, I also treated these as genes, and there just wasn't enough chances for mutation to occur. So at a 0.5% chance, we were seeing, and there's only maybe 16 opportunities for mutation to occur. There just wasn't enough change. In order to see change, I had to crank mutation rate up to maybe 30 or 40%, which is kind of a sign that your genetic algorithm is not working as intended. The fix for this was I still treat each block of room cells and hallway cells as a gene, but during the mutation phase, I iterate through each individual cell within that gene, offering more chances for mutation. So reflection, technical debt. This is easily, by and far, the largest project I did here at Carthage. And as a result, the technical debt that I left behind actually caught up to me this time. Before, I was able to create little hacks to get around everything, but this time, not so much. It works like that. It's like a compounded interest rate. You can get away with it for a little bit, but after a while, it's going to come back and bite you in the butt. And for those that are unfamiliar as to what technical debt is, if you think about it as sort of poor coding practices or quick, shoddy little systems that you put together, things like that often come back. So my design phase. During the design phase last semester, I thought of my design. I thought about it a little bit more, and then I pretty much said this is good to go. I didn't really critically evaluate it. So I would say that was a big lesson. When you design something, critically evaluate it, sleep on it, critically evaluate it again, sleep on it again, rinse and repeat. So in other words, measure twice, cut once. Right tool for the right job. I am not a huge fan of Java as of now. It does a lot. It has a lot to offer, but the lack of being able to deallocate memory was just frustrating to me. There was actually a few times where I thought a program would crash before you ever actually blew up the heap. Turns out, not the case. You can blow up the heap. Anyway, so that was very frustrating, very surreal. So if you're tired of listening to me talk anymore, there's a little slideshow of maps that the internet has rated as 6.5 or better, 6.5 out of 10 or better, or if you have any questions, let them go. Yes?
So genetic algorithms can end up having some really weird results.
Yes.
What was one of the weird results, or some of the weird results you got?
The maze of doors. When during that generation 0, I randomly choose how often we kind of curve the maze. And at one point, it decided 0% we will curve. So it was just straight lines up and down. There was one time where when scattering monsters, or I think it was traps or something around the map, it triggered way too much. So the resulting map after 1,000 generations was almost just like this den of evil, effectively. Yeah, those are probably the weirdest ones that I can think of off the top of my head. Should have collected those, actually. Yes.
Have you playtested any of the final results?
I have not, no. I do not have any friends nearby who usually like to play this game, and with so much going on with finals, it's just too much time commitment to actually play D&D right now. Austin.
What does a Generation 0 map look like? Is it just random noise, basically, or is there
Think, you know, a labyrinth, but there's some squares involved, like large cohesive. I actually should have taken a picture of that. Yeah, think like a normal labyrinth, but there are some like 4x4 rooms somewhere within it. Kevin?
Have you played games like Age of Empires or StarCraft?
Yes.
So you know that like resources have to be in like, these particular areas.
Mhm.
There needs to be like a sense of balance.
Yeah.
So do you think like you could like generalize the algorithm for a map like that?
Absolutely. Some of that is involved right now with monsters being focused within rooms, treasures being focused around monsters, traps being focused with one side of them being towards a room, and the other side being a hallway, so like an entrance type situation. But yes, absolutely, this type of thing could be generalized to create things for Age of Empires and StarCraft and stuff like that. If you have a stronger system, this takes, this is not very pretty, and it still takes 10 minutes to go through 1,000 generations. Anything else? Professor Moni.
Can you get a little more specific about the thing that came back to bite you?
It was a system in the very beginning with class inheritance. So the way cells currently work is there's just a variable inside of them that is, it's just an integer, and there's some globals that you can choose the cell type. I would have liked to be able to, so I did this originally in like a almost prototype testing phase, and then it just stuck around for too long. And then if I wanted to go back and really flesh out these cells, I would have had to change the way so many different systems work and the way changing all of these cells works. So it was just, I let the prototype go on too long, and I should have measured twice, cut once.
So is that, so I've noticed the same thing in object-oriented
Mhm.
programs. They tend to get rigid at some point.
Mhm.
So one of the nice things about functional programs
Right.
is you tend to not have so much interconnection. Do you think you could have done this or something similar in
Functionally?
more of a functional programming language?
I'm 100% sure it's possible. I haven't thought about it, so I couldn't give you a design or anything, but absolutely, I believe it would be possible, because a lot of this is very recursive.
That's
Yeah.
another thing that functional programming
Yeah.
languages are good at.
Mike.
What kind of things did you use to optimize like the method for like generating the new maps and generating new generations? Did you use multi-threading or anything like that?
Yes, there is some multi-threading going on. Turns out multi-threading in Java is kind of a pain. There's just 8 different classes that you need to use. So I found a user-made library that makes it super easy. You pass in the computation as an anonymous function to the class, and then it creates its thread for it, and it works fine. So, yes.
If you had more time, what features would you add to this?
Oops. I would like to do a sort of being able to output the maps as an object file, so you can re-input them at a later time, and sort of, if you want to pass in 3 different files at the same time, you can kind of see what generates with those as the base. If those 3 maps were generation 0 or something, you can see what happens from them. I think that'd be the biggest feature if I could add next. And as well as making it much faster, so I can add it as a web application for other people to use. So, anything else? Oh, Jonah?
What's the most generations you ever ran? It was like 1,000, like the optimal, or like?
No. So 1,000 generations is usually pretty good. I'd say it has a 60% or so success rate. And then the sweet spot seems to be 2,500 to 3,000. Just messing around. I ran it for 50,000 overnight one time, just to see what happened. And it didn't. I mean, at one point, every map within the population was the exact same map. So not a whole lot changed eventually. Yes.
Will you be putting these maps online anywhere so someone can playtest them?
Yeah, probably. What I want to do is, I mentioned that I want to make it a web app, and as of right now, you could dig through Reddit somewhere, and you will find a post by my throwaway Reddit account that just links to a bunch of these and rate my maps.
I'm actually the president of Tabletop RPG on my
Nice.
campus, so shoot a link sometime.
Will do. I mean, I graduate, but yeah, hopefully.
So now we have 2 projects this year using genetic programming.
Yes.
Speaking together, there may be students in the future who are interested in GAs. Do you want to add anything to speaking to the juniors in the room? They were interested in the genetic algorithm base project. What did you find most satisfying about them? What did you find most challenging about them?
So in my experience, the most satisfying aspect was definitely just seeing things change that were changing because of the equation that you have running in the background. The most challenging part is that equation. It got kind of mathy at one point, and then it just became ugly.
Okay, awesome.
If you choose a genetic algorithm for your thesis, I would say probably about 90% of what you do is probably do the fitness algorithm.
Yeah, 100%.
Absolutely right.
100%.
That's basically my entire thesis was just the fitness algorithm.
And it's all math. It's all math.
So hopefully next year there will be an AI course offered sometime.
Yep.
Sorry, seniors.
Yeah.
Yeah, we missed it by a hair.